Okay, welcome back, everyone. Um, we are going to do some more examples today of working with energy problems in various contexts. So, without further ado, here we go. All right, so for our first example here, it says the Intimidator ride at Carowinds has a 211-foot, that's 64-meter drop in its first hill. Assuming that the train is moving very slowly at the stop, how fast is it moving when it reaches the bottom of the hill? All right, so as usual, we can draw ourselves a picture to give us an idea of what's going on. And we have our roller coaster train up here at the top, and then down here again at the bottom. And at the bottom, it's moving very quickly. And at the top, essentially, it doesn't have any motion to speak of at all. We haven't been told anything about friction or whatever, so we're going to assume here that there is no friction in the problem for lack of any other information about it. So lacking friction, the only really important force acting on our system is gravity. Gravity is a conserved force, so this is going to be an energy conservation problem. And our two interesting moments in time are this moment at the top of the hill, when the velocity is 0, but that we have some sort of height, in this case 64 meters above the ground, or above the low point. And the second moment in time is this one right here when we're at the bottom of the hill. And again, if we define the 0 point of our gravitational potential energy to be down here at the bottom of the hill, then our second moment of time here will be this moment when we're moving and we have some kinetic energy but no gravitational potential energy to speak of. So energy is conserved. We can say energy at moment 1 equals energy at moment 2. And the energy at moment 1, I mean, we could write down spring potential energy at moment 1 plus gravitational potential energy at moment 1 plus kinetic energy at moment 1 is equal to spring potential energy at moment 2 plus gravitational potential energy at moment 2 plus kinetic energy at moment 2. And then recognize that most of these are going to be 0. So there are no springs anywhere, so we can set the spring potential energies to 0. At the top of the hill, we're not moving very fast, and so the kinetic energy is 0. And at the bottom of the hill, we're down at the 0 point of our gravitational potential energy, and so we can set that equal to 0. And what we're left with is that the gravitational potential energy at moment 1 must equal the kinetic energy at moment 2. And the gravitational potential energy at moment 1, that's going to be mass times our constant g times the height of our hill, and the kinetic energy at moment 2, that's going to be 1/2 our mass times our speed squared. Conveniently, the masses cancel here, which is good because we didn't know anything about the mass of our roller coaster either. And we want to know how fast it's going, so we're solving for velocity. So we can say that velocity squared is gh, or that velocity is the square root of gh, which is the square root of, oops, we forgot a factor of 2 here. The 2 goes there, the 2 goes there. 2 times 9.8 meters per second squared times our height of 64 meters. And now we get out a calculator. 2 times 9.8 times 64, 1254, and take the square root of that. So our speed at the bottom of the hill is 35 meters per second, at least to two significant figures. Okay, so let's move on to a different roller coaster problem. This one says that modern roller coasters have vertical loops like the one shown in the figure. The radius of curvature is smaller at the top than on the side, so that the downward centripetal acceleration at the top will be greater than the acceleration due to gravity, keeping the passengers pressed firmly into their seats. Part A, what's the speed of the roller coaster in meters per second at the top of the loop if the radius of curvature there is 15 meters and the downward acceleration of the car is 1.4 g's? In part B, the beginning of this roller coaster is at the top of a high hill. If it started from rest at the top of this hill, how high in meters above the top of the loop is this initial starting point? You may assume there's no friction anywhere on the track. And then in part C it says, if it actually starts 4.5 meters higher than your answer to the previous part, yet reaches the top of the loop with the same velocity, how much energy in joules did it lose to friction? Its mass is 1,100 kilograms. Okay, so obviously there are several things going on in this problem, but let us start here. Again, as usual, with a diagram. And so for part A, what we have is that there is some sort of a loop, and that this loop has a 15-meter radius, and that the acceleration at the top of the loop the magnitude of that acceleration is 1.4 g's. So that's 1.4 times 9.8 meters per second squared. And that has to be the value of the centripetal acceleration. And so we can use our centripetal accelerations formula. V squared over r is the magnitude of centripetal acceleration, which in this case is 1.4 g. And we can just use this to solve directly for our speed, the speed we would need to be going at for this 1.4 g's to be the appropriate centripetal acceleration. So in other words, the speed squared is r times the magnitude of the centripetal acceleration, or the speed then is just the square root of r times the magnitude of the centripetal acceleration, which in this case 15 meters times 1.4 times 9.8 meters per second squared. And if we take 15 times 1.4 times 9.8, and then take the square root of that, we find that the speed we must be going at the top of the loop, so we're going to call this the speed at the speed loop, is 14.3 meters per second. All right. In part B, it says the beginning of this roller coaster is at the top of a high hill. So our roller coaster starts up here, kind of like it did in the Carowinds problem. You come down here somewhere. We go through our loop like so, where this again is the top of our loop, where we are moving at a speed v loop, and up here we are moving again at basically zero velocity. So this problem is again very much like the Carowinds problem, and indeed we could make it exactly like the Carowinds problem if we decide to call the top of the loop the place where gravitational potential energy is 0, then this height here between the starting place and the top of the loop, that'll be the height. Again, we have moment 1 at the top of the hill. Moment 2 now is at the top of the loop. And again, we're going to assume here that there's no friction so that energy is conserved. Energy 1 equals energy 2. At moment 1, the only energy we have is the gravitational potential energy, mgh. And at moment 2, the only energy we have is the kinetic energy, 1/2 mv squared. Again, the masses cancel out. And this time we're looking for the height. So that's going to be v squared over 2g. For the velocity, we just put in the velocity we calculated for part 1. That's 14.3 meters per second squared. And on the bottom, twice the gravitational acceleration constant, 9.8 meters per second squared. So 14.3 squared divided by 2 divided by 9.8. And gives us a height of 10.5 meters. In part C, it tells us, well, if the track actually started 4.5 meters higher than our answer, so in part C then, we're saying that we're starting actually, again, the same drawing. And again, we're going to still choose the 0 point of gravitational potential energy to be the top of the loop. We're still moving here at some speed v loop. And we still start from some height above that speed v loop. But now the height is not the 10.5 that we just calculated assuming no friction, but is 4.5 meters above that. So that would be 10.5 meters plus 4.5 meters, or 15 meters above the top of the loop. And now the energy at moment 1 and the energy at moment 2, we can't assume that they are conserved because we're being told that, in fact, friction is a thing. So what we can say instead is that the work being done by friction, the work being done by our non-conservative forces, is going to be the change in the energy. That's going to be our final energy, moment 2, minus our initial energy, moment 1. Again, at moment 1, the only form of energy we have is gravitational potential energy, and the only form of energy we have at moment 2 is kinetic energy. So that's 1/2 m v loop squared for the kinetic energy at moment 2, minus the gravitational potential energy at moment 1, which was our mgh. This time we've been told the mass is 1,000 kilograms. And we want to know what we're solving for here is the change in the energy, or the work being done by friction. How much energy did we lose? So we just start plugging things in. That's 1/2 1,000 kilograms. Again, our speed is 14.3 meters per second. Square that, minus 1,000 kilograms times 9.8 meters per second squared, and our height of 15 meters. So 14.3 squared times 1,000 times 0.5. That's 102,245 joules minus 1,000 times 9.8 times 15, 147,000 joules. So this is the work done by friction here is going to be minus 44.8 kilojoules. All right, so if we started at 15 meters, not at the 10.5 meters, then in going down there and arriving at the same velocity we had before, then we must have somewhere along the line lost about 45,000 joules. Okay, well, let's try another one here. This one says, a pogo stick has a spring with a force constant of 2.5 times 10 to the 4 newtons per meter, which can be compressed 10.4 centimeters. To what maximum height in meters above the equilibrium position of the spring can a child jump on the stick using only the energy of the spring if the child and the stick have a total mass of 38 kilograms? And how fast are the child and the stick moving when the spring returns to its uncompressed position? All right. So these vertical spring compression problems can be a little bit tricky because you have to be careful to be aware of exactly what's being asked. So, for instance, let me illustrate that in this case. In this case, what we have to draw our picture very carefully, right? So, the pogo stick here is being compressed by our distance here. I'm going to call it delta y, between the compressed and the uncompressed point. And so in that, going from the uncompressed to the compressed, then we are definitely engaging in some spring potential energy. But we also have to remember that the altitude here is changing. And so not only has the have we changed the spring compression energy or the spring potential energy, but we've also changed the gravitational potential energy. This particular problem is asking us to calculate height in meters above the equilibrium position of the spring. And so we have a choice as to where we're going to define the 0 point of gravitational potential energy. We could either define it relative to the 0 point of, or relative to the elastic potential energy's 0 point. In other words, we could define this position right here, the uncompressed spring position, as the 0 point of gravitational potential energy, in which case at the maximum compression we would have negative gravitational potential energy. Or perhaps we want to define the bottom point here, the compressed point, as the point of our 0 of gravitational potential energy, and then by uncompressing we have gained a little bit of gravitational potential energy. I'm going to guess that it's maybe less confusing to assume that the lowest point is the 0 point of gravitational potential energy. So let's go ahead and just say that here is where we're going to set UG equal to 0. But we could also have done that up here. All right, so our moment 1 is when we're fully compressed and we have 0 gravitational potential energy but non-zero spring potential energy. 1/2 k times, in this case, our delta y squared. And then it asks us to what height in meters above the equilibrium position. Right? So it wants to know how high, where the height is defined here as the distance between the equilibrium position and our maximum height up here with our uncompressed pogo stick string, like so, and of course our person on our uncompressed pogo stick in both cases. Again, apologies for the crude cartooning here. Where again we're measuring a height above that point. So at this point 2, we have only gravitational potential energy. But how much gravitational potential energy do we have? Well, we have height plus that delta y versus of altitude above our 0 point of gravitational potential energy. And so our mg times height plus delta y will be the total amount of gravitational potential energy we have up there. Here at moment 1, we have only spring potential energy. Here at moment 2, we have only gravitational potential energy. And we're going to conserve energy between them, so we can say the energy at moment 1 equals the energy at moment 2. So 1/2 k times delta y squared is equal to mg times h plus delta y. And now we can solve for the thing that we're looking for, in this case, our height h. And so let's go ahead and expand this out as mgh plus mg delta y. And we can pull the delta y term over, 1/2 k delta y squared minus mg delta y equals our mgh, and we can divide both sides over here by mg, so 1/2 k delta y squared minus mg delta y over mg is our height. We can simplify this left-hand side a little bit. Just k over delta y squared over mg minus delta y is our height, and now we can start plugging in numbers. So our spring constant is 2.5 times 10 to the 4 newtons per meter. Our delta y is 0.104 meters squared divided by our mass, 38 kilograms, and g, 9.8 meters per second squared, minus 0.104 meters equals our height, 0.10 squared times 2.5 10 to the 4 divided by 38 divided by 9.8. That's 0.726 meters minus 0.104 meters gives us a height of 0.622 meters, or 62.2 centimeters. So that's how high we could get above above the equilibrium point. And we had to be careful here, again, to keep track of where we were setting the 0 point for our gravitational potential energy, and then making sure that we use that same 0 point at both positions. In part 2 here, it asks how fast are we moving when the spring returns to its uncompressed position. So now we have, again, our compressed position here. Where we are compressed by our delta y. That's our moment 1, where all the energy, again, is spring potential energy, 1/2 k delta y squared. And we're defining this point here at the compressed point where the gravitational potential energy is 0. Our moment 2 is when we reach the uncompressed point up here. And now we have 0 spring potential energy, but we're moving at some speed, and we have some non-zero altitude. We're at a height of delta y above our 0 point, and so we have some gravitational potential energy, mg delta y, and some kinetic energy, 1/2 mv squared. At moment 2, again, we're going to conserve energy, so we say energy at moment 1 equals energy at moment 2, and we write down the terms of energy that we have at each place. So energy at moment 1, that's 1/2 k delta y squared. Energy at moment 2, that is 1/2 mv squared, our kinetic energy, plus a little bit of gravitational potential energy, mg delta y. We're solving for velocity, so let's go ahead and move the potential energy term over here to the left. So 1/2 k delta y squared minus mg delta y is 1/2 mv squared, and we're solving for speed, so we can multiply or divide by 1/2 m on both sides, so that's going to give us k over m delta y squared minus g delta y over 2, no, minus 2g delta y, so multiply by 2, divide by m, is v squared. So v, our speed, is going to be the square root of k over m delta y squared minus 2g delta y. And we can plug in some numbers. Again, our spring constant k here is 2.5 times 10 to the 4 newtons per meter, divided by our mass of 38 kilograms. Our delta y is 0.104 meters squared minus 2 times 9.8 meters per second squared times, again, our delta y of 0.104 meters. Take that whole business and stick it under the square root. 0.104 squared times 2.5 10 to the 4 divided by 38 That's the square root of 7.16 on the left minus 2 times 9.8 times 0.104, 2.04. Both of these are meters squared per second squared, meters squared per second squared. So 7.16 minus 2.04, take the square root of that, and our speed is 2.26 meters per second. All right, so again, the trick here with these vertical spring problems is to make sure we are very careful about wherever we pick to be the 0 point of gravitational potential energy, and make sure that we understand how, as the spring relaxes, the gravitational potential energy also has to come into effect. All right, let's try another one. This one says, an ideal pendulum of length 1.1 meters supports a mass of 0.5 kilograms. Initially, the pendulum is lifted such that it makes an angle of 27 degrees with respect to the vertical. When the pendulum is released from rest, what is the maximum speed in meters per second that the mass reaches? All right, well, let's draw ourselves a picture. Always, always useful. So our first moment is going to be this one here, when our pendulum of length L is pulled out by this angle here, theta, from the vertical. And it has a mass m. There's no motion, so velocity equals 0 at this point. And we're just suspended from the ceiling there. Okay, this is our moment 1. And our second interesting moment is the moment here, when we're now at some length L straight downward, and we have our mass like so, and now we're moving at some speed v. This is our moment 2. And the question is, where are we going? So first of all, what's going on? All right, so we have only gravity at work here. Okay, that's the only force that's going to be doing any work. There is a force of tension in the string, but the string's tension is always going to be perpendicular to the motion of our mass, and so the string isn't doing any work. Therefore, gravity is the only thing that could be doing any work, and so since gravity is a conservative force, we can use energy conservation. We need to define our 0.4 gravitational potential energy. Again, we could define it here as this low point, UG equals 0, in which case, again, the energy at moment 1 is going to be all gravitational potential energy, mg times whatever the height is above our lowest point. And the energy at moment 2 is all going to be kinetic, 1/2 mv squared. And so the question is, how high is our mass suspended at moment 1? And this is where we need a little bit of trigonometry. So we have a situation here where this is a length L, and this theta here is our 27 degree angle. Our length here, 1.1 meters. The height we care about is that height there, where this length is also 1L. And so the question is, how long is that? Well, that distance, that's L cosine theta. And so this height is L minus L cosine theta. It's the difference between this length and the whole length there. And so we can go back to our energy conservation, E1 equals E2. E1 is mg times our height, which is L minus L cosine theta. And that's got to equal our energy at moment 2, which is 1/2 mv squared. The masses cancel on both sides. Let's go ahead and factor out the L here. So that's g times L times 1 minus cosine theta on the left. And on the right we have v squared over 2. We're solving for speed. So 2gl times 1 minus cosine theta is our speed squared. So our speed is the square root of 2 times g, which is 9.8 meters per second squared, times our length, which is 1.1 meters, times 1 minus the cosine of 27 degrees. All right. 1 minus the cosine of 27 times 1.1 times 9.8 times 2. Take the square root of that whole thing. Our speed is 1.5 meters per second. All right, that's where we're going to end off for today. On our next lesson, we will have a couple more examples. We'll talk about one more aspect of energy, and then we might also do a few practice problems from the forces chapters, sort of as a little bit of review for our upcoming exam number 2.